Alright, so today we're going to be learning about section 5.4, inverses of functions and relations. So we're going to talk about inverse of relations, inverse functions and the horizontal line test, and finding the inverse of a function. So inverses. In general, we use the word inverse to indicate the idea of undoing something. For example, what would be the inverse of putting on your shoes, of opening a door? Some of the operations are easier to undo than others. For example, the inverse of opening a door would be closing it. That's pretty easy to do. The inverse of putting on your shoes is taking them off. Sometimes you design the inverse to be easier to do, like with tying your shoelaces. Untying your shoelaces is easier than tying them, and that's by design. Some operations are easier to undo than others. What would be the inverse of tying your shoes or of mixing a cake? So the mixing a cake one, that inverse, you can't undo making a cake, not in any reasonable amount of time or fashion or any process we know. It's like mixing paint. Once you mix two colors of paint to make a new color, unmixing them is almost impossible. So some inverses are easy by design, like the inverse of tying your shoes, untying them. And some of them are impossible, are impossible with what we know now. We are interested in inverses in a mathematical sense. For example, what would be the inverse of adding 2 or of multiplying by 2? So the inverse of adding 2, of course, would be subtracting 2, and multiplying by 2 would be divided by 2. When we want to define the inverse of a relation, we want to find which input gives us a specific output. We do this by defining a new relation where we change the inputs x and outputs y. For a relation r, we call the inverse of the relation r to the negative first power. So this comes from the inverse like in mathematics, or inverse like for exponents, where the multiplicative inverse, when you multiply 5 times 1/5, in this example, you get 1 back out. But the negative 1 in this case does not mean the reciprocal, all right? So we're borrowing the notation from multiplication and exponents, but this negative 1, when you see something that's not a number to the negative first power, if it's a function, if it's a relation, then we're talking about the inverse. So r to the negative first power, or r inverse, equals, and so we have b comma a for every a, b, and r. So in other words, for every pair a, b, and r, the ordered pair b, a is in r inverse. Because we exchange the x and the y, we also change the values of the domain, the x values, and the range, the set of the y values. So we switch the domain and the range, essentially. So for this first exercise, it says determine the inverse of each of the following relations, then graph its relation and its inverse, and determine the domain and the range of both the relation and the inverse. So right here, for part A, r equals, and we have the points 5, 7, 6, 2, 6, 3, and 2, negative 1. Those are our 4 points. So r inverse would be equal to the set. We use curly braces when it's a finite number of things, or we're using a rule to define something. So if 5 went to 7, 7 has to go to 5. So 7, 5. And if 6 went to 2, then 2 goes to 6. And 6 goes to 3, so 3 goes to 6. And then we have 2 goes to negative 1, so negative 1 goes to 2. And that's our inverse. And we were to graph this, it would just be a bunch of points on a grid. So we'd have, let's do a different color for the original. We'll do purple for the original r. So we go over 5, up 7, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, way up here. And then we'd have over 6, up 2, so over 6, up 2, over 6, up 3. And then the last point, over 2, down 1. So that would be our original r. Our new r inverse, we would go over 7 and up 5. So 1, 2, 3, 4, 5 would be right here. And then we'd go over 2, up 6. So 6 would be right here. And we'd have over 3, up 6, which would be right here. And the last one, left 1 and up 2. And one thing we'll notice is that this is actually, I'll just cover the pens I need when I need them. We'll see later that this is everything's been reflected across the line x equals y. You can see that this point, this original point, purple point, moved here. This one moved here. This one moved here. And this one moved over here. So it got reflected across the line x equals y. We'll talk more about that later. Next, it says determine the inverse of each of the following relations and graph the relations. So it's the same instructions because the exercise continue. Oh, I forgot to say the domain and the range of each. Oops. I knew I forgot something. I always do that. So let's say in the original one, so we have the domain and the range. So the domain in the first one, we have 5, 6, and we only have to write down once because it's a unique element that occurs in the domain, so we don't need to write 6 down twice. And 2, and so that's our domain, and our range was 7, 2, 3, and -1. And all we have to do is switch our domain and the range. So this is our range of our inverse, and this is the domain of our inverse. So we just switch them. So see the range, the domain was now 7, 2, 3, -1. And the range is now 5, 6, and 6 happens twice, and then 2. So we just switch our domain and our range. Next, we do the same thing for our second example B here. We have y equals x squared. So the easiest way to do this is basically the inverse would be you just switch the x and the y's, so that would be x equals y squared. But that's really hard to graph, so the easiest thing to do is you have your you have your x column, your x squared column, or basically your y column for this right here. Let me do this in a different color. And so you would just normally graph this like a parabola. So you have 0, 0 squared is 0, -1, 1, -2, 4, 1, 1, and 2, 4. So those would be all your points. Now, for us, we'd switch it. So our domain becomes our range. So we're going to label this column right here as our, so this is going to be our y. So this is our, we reverse these. So this would be our, I'm mixing up my colors. So this is our domain. Well, let me write the points out. It'd be easier to see if I wrote the points out. So -2, 4, -1, 1, 0, 0, and 1, 1. Now there's a lot of points. I'm just listing a finite number of ones so we can see it to graph. So I'm going to go over here and graph this parabola. I'm going to go over 1, up 1, 1, 1, 2, up here. So this is 0, 0. Oh. Assume it's a nice symmetric parabola. And so the easiest thing to do is just switch these points to the inverse and just say, I'm going to switch my domain and my range. So I'm going to take 4, -2, 1, -1, 0, 0, 1, 1. And notice those don't switch because those are the same numbers. 4, 2. So I'm going to go graph these points now. So I'm going to graph the point 0, 0, 1, 1. And then I'm also going to graph the point 1, -1. So I'll be down here. And then I'm going to graph 4. So I'm going to go up, over 4, right 4. And down 2. And then I'm going to go over 4 and up 2. So I'm going to have this parabola line on its side. So it's not like it fell over. Remember, we're going to talk more about this later, but it's reflected across the line x equals y. It's a good time to see it because we're drawing these visually. And so if we were to say our domain and range, well, for the whole thing, we'd say for the original, the domain and range for parabola. The domain would be all real numbers. I can plug anything in for x. And the range, the y values I get back out, well, I'm going to restrict it from 0 to infinity. And then so for my inverse, this becomes, all real numbers becomes my range. So I get all y values back out. You can see how it's going to increase and decrease on the y-axis forever. But my domain is limited to only positive numbers, because there's no way I can get a negative number back out for x when I'm plugging in values for y. And so you can see this here. So my domain and my range switch. Next it says determine the inverse of the relation where we have y equals negative x, negative absolute value of x plus 2. And it says find 4 points contained in the inverse, find the domain and the range of the inverse. So when Hawks will ask you to do this question, so the easiest way to do it is just switch your x and your y's. So I'm going to say x equals negative absolute value of y plus 2. So I've found the inverse, right? But it's in terms of x and y. And normally we're used to plugging in for x and solving for y. That's just how our brains work. So it says find 4 points contained in the inverse. When you find a function, if you need to find 4 points in the inverse, find 4 points in the original function right here. And then just switch them to make them the 4 points in the inverse. So in other words, some numbers I can plug in for x would be, so let's just say, let me make a chart, that'd be easier. I'm just going to do all these steps at once. So if I plug in 0, the absolute value of 0 is 0 plus 2, and that's going to give us 2 back out. If I plug in something like, this is the absolute value reflected and shift up by 2. We learned that from a previous assignment, I think 5.1. And so I have the lowest point, or the highest point in this case, because it's been reflected across the x-axis. And then so plotting in negative 1, well, that'd be 1. That'd give me positive 1, minus 1, plus 1, 1 back out. And if I plug in positive 1, I should get the same answer, which I do, 1. So if I'm looking over here, I need 4 points, so let's do one more. So let's plug in 2. So the absolute value of 2 is 2, negative 2, and then plus 2 gives me 0 back out. And it doesn't ask us to graph it. So these are 4 points in the original function. So I just take these points and I just say, okay, I'm just going to reverse them for my inverse, reverse the order. And now I have 4 points in the I have 4 points in the inverse. So you do whichever one's easier. You know, if for example they gave you this problem right here as your function, it said find 4 points in the inverse, then we would just find 4 points in the inverse because that would be the easier function to look at. But if they give you this function and then you find the inverse that says find 4 points, it's easier just to find 4 points in the original function and then just switch the points around. And so the domain and the range, we can see that this is going to be the original graph. So the domain and the range. So let's sketch the original graph. We said it was moved up 2 units and reflected down. So like this. And so the domain of the original, range of the original. So the domain was all real numbers, negative infinity, positive infinity. And the range looks like it's going to go from negative infinity all the way to 2, since it's been turned upside down, including 2. And we can see that max value there. And then we're going to switch it and we're going to say the range of our inverse is going to be all real numbers. And the domain of our inverse is going to be restricted to negative infinity to 2. And like I said, you pick whichever one's easier. If they give you this as the original function, go ahead and find the inverse, and then it's easy to see which one it is. If they give you a nice function and the inverse is not in terms of y equals something, then do the trick where you just switch everything. It's easier to find stuff for whatever y equals. Use that equation. If it's the original equation, use the inverse. Or sorry, if it's the original equation, do it for that, then the inverse. If this was the original equation, just take the inverse and do it normally. One-to-one functions. So remember that for a relation to be a function, each input x can only correspond to a single output y. If there are no two inputs of a function f of x that give the same output, we say the function is of one-to-one. In other words, I don't have any repeat y values. We can also say that f of x is a one-to-one function, more formally, if f of x is one-to-one whenever x1 does not equal x2, you have two different x coordinates, then we know that f of x sub 1 is not equal to f of x sub 2. In other words, our y values can't match. For any two x values that are not the same, our y values can't match if they're one-to-one. Graphically, a one-to-one function will pass the horizontal line test. That is, the horizontal line will never intersect the function twice or more than once. You can say it either way. So the reason why this is because if we have a parabola here, it fails the horizontal line test, because if we look at its inverse, like we graphed a little while ago, that horizontal line becomes the vertical line and it will fail the vertical line test. So that means that x equals y squared is not a function. Because the original function doesn't pass the horizontal line test. So we'll see some examples of that in a minute. If x is a one-to-one function, then each output y will only have one output x. When we interchange x and y, we find the inverse of each input x will only have one output y. This means that f inverse will also be a function. Because f passes the horizontal line test, then f inverse of x will pass the vertical line test. And essentially what I showed you there. So determine whether following functions have inverse functions. So the easiest way to do this is graph the original function and see if it passes the horizontal line test. It's kind of hard to prove something's one-to-one generically. It's just not an easy task to do normally, because you have to consider all the points. So it's easier just to look at the graph. So if we look at the graph of the absolute value of x, there's that V shape here. Well, we can see right here, we draw a horizontal line, it fails. So it fails the horizontal line test. It is not one-to-one. In other words, its inverse is not a function. Next one here, we have a graph that's a cubic graph that's been moved. When we add to the inside, we move left. So I'm going to go 1, 2, 3, and then we're just going to graph that cubic graph. We've been graphing for a while. We've been practicing this. It's going to look something like that. This is just a rough sketch. And you can see when we draw horizontal lines, it's going to pass at every point. So it passes horizontal line test. It is one-to-one. And its inverse is a function. All right. So knowing the rough sketch of graph can help you find the inverse and tell if it's have an inverse. Usually if you try to solve it for an inverse, and we'll do that here in a second, you'll get some weird stuff back out. I'll go over more here that in a second. So finding the inverse function formulas, there's a general procedure for finding inverses of the functions defined by formulas. We let f of x be a one-to-one function defined by formula. So if they ask you to find an inverse, it's either going to have an inverse and it's easy to solve, or you can just leave it in its x swapped y format. But if we're going to call it a function, then we need to do the following. We change f of x into y in the formula. This will give you an equation involving x and y's. We exchange x and y in the equation. In the third step, we solve the new equation for y, and then we change the y in our new formula to f inverse of x. So let's see how that goes. So let's just think about this rationally. So this function takes a number, multiplies it by 6, and then subtracts 1 from it. So if it's the inverse, not only is it going to do the opposite actions, but it does them in a reverse order. So if I multiplied by 6 and then subtracted 1, I should add 1 and then divide by 6. So let's see if that's what happens. So the first step, I'm going to change this to y equals squared 1. And then the second step, I'm going to change x and y. And then in the third step, this is the longest step, solve for y. And so we're going to move the 1 to the other side, and we're going to have x plus 1 equals 6y. And then I'm going to divide both sides by 6 to get the y by itself. So I'm going to have x plus 1 over 6 equals y. And now the fourth step, I'm going to change y to f inverse. So I'm going to have x plus 1 over 6 equals f inverse of x. And when I do that, usually we write the f inverse of x. The property of equality means that we can just, switch them across the equal sign at the same time. And typically that's how we write. One way you can check just to see if you got in the right ballpark. Now, this won't work for every number you pick, but it should work for a decent number. This is nice because any numbers I plug in, I'll get real numbers back out, or all real numbers back out for, its domain and its range. So if I want to check, I can plug in something like f of, let's just say 0, into our original equation here, and we'll get 6 times 0 minus 1, and that'll give us negative 1 back out. So if this is the inverse, right, I should be able to take f inverse of negative 1, and I should get back out what I started. And so if I go in the formula here, and I say that f inverse, that's going to be negative 1 plus 1 over 6. That's going to give me 0 over 6, which is 0. So yeah, 0 went to negative 1, so negative 1 went to 0 in our problem. So that's just a quick check. Remember, that's just a spot check. You could actually get a point on a line, like, you could plug in 1 and it gives you 1 back out, and now that doesn't help. But yeah. So here we have a new equation. So same instructions. So just a quick review. We need to change f of x into y, switch our x and our y, solve for the new y, and then write our new y as f inverse of x. In this case, we use g of x. So I'm going to change that g of x. So the first step to y, I'm going to get 5 over 3x plus 2. That's my g of x. So my second step is going to give us, well, we're going to switch our x and our y. So we got x equals 5 over 3y plus 2. And so now the third step is going to be to solve for y. And now I have to do a little bit more work here because I have to get this y out of the denominator. So I'm going to multiply both sides by 3y plus 2. And then here's two ways you can do it. You can distribute this x, which you'll need to do if you have more x's on this side and you got all the x's one side because you may have an x in the numerator as well. Or you could just divide by x. I'm going to do it the long way. For example, if there was an x over here, it'd be better to do that way. So I'm going to say x, and that's going to give me 3xy plus 2x equals 5. And so what do I need here? I'm going to move that 2x to the other side so I get all my y terms by themselves. So then I'm going to get 5 minus 2x, and then I'm going to divide everything by 3x. So I'm going to get y equals 5 minus 2x all over 3x. Now this can be rewritten, and I can write this as the following. I can say that it's going to be y equals 5 over 3x minus, and then I can have 2 over 3, and my x's would cancel because I'm just taking each term divided by this monomial. And so you can get either way. So the answer will be f, or in this case g inverse. So our fourth step is going to be g inverse of x equals 5 over 3x minus 2/3, or it should take the other answer as well. It should take either one. And once again, you can spot check it. You could, for example, real quick if you just want to see. Trying to think of a nice number to plug in. 1 would probably be nice, so I'm going to say g of 1 would give me 5 over 3 times 1 plus 2, which would give you 5 over 5, which is 1. So actually, that's not a really good number, because if you plug that in, essentially all you're going to get is this already lies on the line. Wherever this graph is, this actually has the 0.11 on it. So that's not super helpful. So that's not a nice number. What's another nice number we could probably pick? I don't know. It'd probably have to be a fraction, though. So let's just go with 0. So g of 0, that'd be 5 over 0 plus 2. So I'd get 5 halves back out. And then if I plug it, let's plug it into this one. So we'd have g inverse of 5 halves would give us 5 minus 2 times 5 halves all over 3 times 5 halves. And so when we do that, we can see in the numerator what we're going to get is we're going to get 5 minus 5 all over 15 halves. And so I'm going to get 0 back out, which is what we, so 0 went to 5 halves and 5 halves went to 0. So that's a way of checking it. Like I said, it's something you do on a test. The easiest way to check it would be a graph on a graphing calculator, this one and that one. You just see the reflector across the line x equals y. So some properties of inverses. If we do something and then undo it, we should always end up where we started. And that was the point of the checking. We have a function f of x with an inverse, f inverse of x. They satisfy the properties. If f of f inverse of x equals x for all x in the domain of f inverse of x, and f inverse of f of x equals x for all x in the domain of f of x. Note this is not true, then f is not 1 to 1. So for example, if we take a number and square it, and then take the square root of it, well, we're going to get 4 squared, so in this case negative 2 squared will give us 4. Square root of 4 is 2, it's not equal to negative 2. That's because x squared is not 1 to 1. But it's basically saying if I compose two functions together, if I compose f with its inverse, it's an open, let me do it again. F composed with f inverse of x should always give you x back out. All right, so let's do this. I'm going to do this one way and leave the other way to the reader. But let's do it the first way. So I'm going to compose f with m inverse and the following relationship, that would give us x. So I'm going to do this part. And then compose in the other direction for equal to x for the function. And I have f of x equals x minus 1 quantity cubed plus 2 and f inverse. And so they've given us f inverse. We don't have to find it. F inverse of x equals x minus 2 quantity to the 1/3 plus 1. So it makes sense. We see some of the same numbers, some of the same reciprocal exponents. So it makes sense that these would be inverses of each other. But I'm going to say f composed with f inverse, or f of f inverse of x. And let me try to clarify this by writing this in blue. And I'm going to write f of x in purple. So that's going to be the goal. So I'm going to have f of, and then in parentheses, let's see if I can keep my colors straight here. And then in parentheses, I'm going to plug in, what do we actually have? X minus 2 to the 1/3 plus 1. And then that's going to be plugged into f. And what was f? F said the following. It said, I'm going to take my function, and I'm going to use double parentheses here. And I'm going to plug in x minus 2 to the 1/3 plus 1. I'll close up that parentheses. Then I'm going to say minus 1 to the 1/3 and then plus 2. So notice my parentheses all match here. And so the purple function, that's f, and the inverse is the blue function right here. And then we're going to start getting rid of our parentheses and doing the math here. So I'm going to take away these parentheses right here, and when I do that, I'm going to get the following parentheses x minus 2 to the 1/3, and the plus 1 and minus 1 cancel out, so that's the end of that function. And then I'm going to have all this raised to the third plus 2. Then if I raise something to the 1/3, I'll raise to the third. Well, that'll just give me my x minus 2 back out plus 2, which will give us just x back out. And so as we compose these functions, we can see how the function would just collapse down into x, essentially. And the same thing is true if we went f inverse of f of x and that equals, so I'm just going to set this up, but basically it does the same thing. It all collapses down, and then I'm going to plug in what's my original f. It's x minus 1 to the third plus 2. And so I'm going to now get double parentheses x minus 1 to the third plus 2. And then I'm going to close that up here. And then what do I have here? I have this to the 1/3. No, minus 2 to the 1/3 plus 1. I have the right number of parentheses? I think I have. I feel like I have an extra set of parentheses here. It all matches. Okay. Yeah, and then you just, once again, you just keep going, and then that'll eventually come down to x again. So if you compose two inverses, an inverse with itself in either direction, you should get x back out. The order doesn't matter when you compose inverses with each other. And looking at it, a graph of it might be a little bit easier to see. So we have our, let me make sure I keep my notation the same, our f inverse was blue, our f of x was purple. And so the purple one here would be this line right here, the cubic function graph. And this would be the cube root function graph, and the basic function graph. Notice that the graph is a reflected image across the line x equals y. We talked about that earlier. So you have this nice reflection. You can see at some point they have the same point right here somewhere between 0 and -1. And this is because the inverse is found by switching x's and y's. So so if you look at specific points, you wanted to make sure, like example, the original function had the point 0, 1 on it. Well, the inverse has the point 1, 0 on it. And so that's just a couple things, like this is the point 1, 2. The inverse would have the point 2, 1 on it. All right. So that's it for inverses for today. Hope you all had a good one. Talk to you later.